Today I will talk about lead dichromate titanate, which aka PZTs. You may not familiar with this term, but you may should familiar with ceramic. A ceramic, a ceramic is any of the various hard, brittle, heat-resistant, and corrosion-resistant materials made by shaping and then firing an inorganic, non-metallic material. And the history of ceramic can trace back to 26,000 years ago. And in ancient, you can see like the pottery, clay, also this one is made by ceramic materials. Also in China, there's like a very famous artifact called blue and white porcelain. And you may ask why this relate to PZT. So the truth is PZT is one of the ceramic materials, and it has a really important properties called piezoelectricities, which I will introduce it in detail later in next sections. And in 1818, brothers Curie and Jacques Curie discovered applying pressure to crystals such as quartz, tourmaline, and roseate cells generate electrical charges on the surface of these materials. In 1881, Gabriel Liebman finds the converse in fact that the application of an electrical field to this material causes the internal generation of a magnetic string. And the discovery of piezoelectricity generate significant interest in the Europe scientific community, and piezoelectricities developed as a new field of research in the last quarter of the 19th century. And PZT is invented by Tokyo Institute of Technology around 1952, and you can see this in nowadays like televisions, your phones all have this important ceramic materials involved in there.
Now, one of the most common questions we get is, how do we actually apply PZT? How can we actually use it? Now, PZT is one of the main parts of a component called an ultrasonic transducer. An ultrasonic transducer is specifically a machine which can convert electrical energy into ultrasonic waves. This component can be utilized into a larger machine called an ultrasound. An ultrasound can be used to do anything from looking at a developing baby to finding any kind of abnormalities in the body. However, that's not the only thing that PZT can be used to do. Another emerging field is the field of non-destructive evaluation, where ultrasonic waves are used to precisely evaluate the integrity of vehicles, ranging all the way from cars to space vessels, by finding minute flaws that would be otherwise undetected by the naked eye. But however, PZT isn't just limited to biomedical research or evaluation research. It can also be used in aviation technology. Now, anti-flash goggles are designed to turn opaque in case of bright flashes from explosions from enemies. Speaking of which, cheese.
Now that you have seen so many applications of PZT, you may wonder how it is made. The making of PZT components and other similar structured perovskites are relatively easy in the chemistry part. The raw materials are just metal oxide, and the reaction is very simple. First, they are weighed in stoichiometry proportion. Commonly, the molar proportion is 1:1 between zirconium and titanium, but there are variations for different purposes. Then the mixture is put into a ball mill to ensure they are homogeneously mixed. A ball mill that can be as small as a backpack for lab testing or as large as truck for industrial propulsion. After that, they are put into a calciner or a huge furnace that goes to 1000 degrees C or higher. The furnace is where the reaction happens, and after a few hours we could get PZT ceramics with a high conversion. As opposed to organic synthesis that needs strong driving forces, the yield is very high. The next step is to grind it down again and press into desired shape. Use physical vapor deposition techniques to deposit microelectrodes on it to make it able to fit into the circuit. Now that is very interesting part, polarization. Remember the small unit cells that are distorted? Because this material is ground to powder and reshaped, the unpolarized piece of PZT material will have the distorted axis to any possible directions. Thus, the purpose of the polarization is to align the distort axis to the same one, so that the piezoelectric effect of each molecule is added up. To polarize it, a large DC current is needed to pass the material for a while, and a common way to achieve that is to put in silicon oil with a large DC field. Now that the electrode is printed and the material is polarized, we've finished making the PZT element, and it's now electric engineer's job to design the circuit with PZT inside. Now, what is piezoelectricity? Let's start with simple concept in the macro world. Look at this. This is a cute seal plush. If I squish it, that means I put stress on it. It will constrain on the one side and extend on the other. Or in other words, there will be a strain corresponding to the stress. Piezoelectricity is when you put a stress in a piezoelectric material, there will be a current response. Say, if I squish the plush, there will be a current flowing through one of my arm to the other. What exactly happens inside? Let's dive into the molecule and take a look. Every chunk of piezo material, the piezoelectric material, is made up with small molecules. This is a unit cell of PZT molecules we are talking about. The cations at the center can be either titanium or zirconium, and the cations at the corners are lead. The anions at the face center are oxygen atoms. That cube is really tiny with a lattice diameter of only about 4 angstroms. Now, those cubes are not perfect cubes. One of their axes are lengthened by about 0.1 angstrom in room temperature, and the central atom is shifted from the center. This is called non-central symmetry. All piezoelectric materials are non-central symmetric. If the stress is applied against the shifted axis, the lattice parameters and the position of the central atom will further change, leading to a current to the shifting direction of the cation. Now, imagine the tiny current multiplied by the numbers of the unit cell in the bulk material. That makes the current in the seal plush. This GIF here is actually showing the reverse piezoelectric effect. It is the other way round. If you pass the current through the material, the central atom will shift, leading to the deformation to the whole molecule and further the material.
As we delve deeper into the world of PZT, or lead zirconate titanate, it's crucial to understand both its limitations and the exciting future that lies ahead. Let's start with the challenges. One of the primary limitations of PZT is its temperature sensitivity. The Curie temperature, typically ranging from 150 to 350 degrees Celsius, sets an upper limit for high temperature applications. Beyond this point, PZT loses its piezoelectric properties. Even below the Curie temperature, PZT's performance can degrade as temperatures rise, affecting its reliability in certain environments. Another challenge lies in the material's behavior under stress. PZT exhibits creep under constant stress, which can affect its long-term stability. This means that over time, the material may slowly deform, potentially impacting the precision of devices that rely on it. Additionally, PZT displays hysteresis in its strain-electric field relationship. This nonlinear behavior can complicate precise control in some applications, requiring sophisticated compensation techniques. Environmental concerns can also cast a shadow over PZT's future. The lead content in PZT raises significant health and environmental issues. As global regulations tighten around the use of lead in consumer products, this poses a challenge for widespread PZT adoption in certain sectors. Lastly, we must consider the aging effects of PZT. Over time, there's a gradual change in its properties, necessitating periodic recalibration of devices. This aging process can affect the long-term reliability and accuracy of PZT-based systems. However, these challenges haven't dampened the enthusiasm for PZT in the scientific community. In fact, they've spurred exciting research and development efforts. Looking into the future, we see PZT expanding into new applications. One promising area is energy harvesting from ambient vibrations. Imagine sidewalks that generate electricity from footsteps, or bridges that power their own monitoring systems from traffic vibrations. PZT is also finding its way into wearable technology and the Internet of Things devices, opening up new possibilities for smart, self-powered sensors. Ongoing research is addressing PZT's limitations head-on. Scientists are developing lead-free alternatives with potassium-sodium niobate-based materials, showing particular promise. These could potentially offer similar performance to PZT without the environmental concerns. Nanostructured PZT is another area of intense research. By manipulating the material at the nanoscale, researchers aim to enhance its properties, potentially increasing its sensitivity or operating temperature range. As we look into the future, it's clear that while PZT faces challenges, its potential remains immense. The ongoing research and emerging applications promise to keep PZT at the forefront of piezoelectric materials for years to come. Whether it's in its current form or in new innovation variations, PZT will undoubtedly continue to play a crucial role in shaping our technological landscape.